students, good morning. I hope all of you fine now. Today we will discuss here the topic is Cauchy-Reimann equation in the complex integration chapter. So for civil, mechanical, electrical, PC, first year, second semester students, the subject code is BS-M-202. Okay. So first of all, Cauchy-Reimann equation, there are two theorems, theorem 1 and theorem 2. First theorem is a necessary condition for fz to be analytic. The necessary condition for w equals to fz is a function is complex function fz is a u plus ib to be an analytic, that is a differentiable exists. All of you know that if the function differentiable exists, then the function is called an analytic function. At any point it is complex number, so z equals to x plus I by form of its domain D is that the four partial derivatives here del u del x, del u del y, del b del x and del b del y. Because our fz equals to u plus ib form, our u del u is our real part and b is our imaginary part. So here del u del x, del u del y, partial derivative with respect to x, partial derivative with respect to y, function u, this function u, this is partial derivative with respect to x, function is b, and partial derivative with respect to y, function is b. These four partial derivatives will be exist here, and the Cauchy-Reimann equation also satisfied. Here the Cauchy-Reimann equation form is del u del x equals to del b del y and del u del y equals to minus del b del x. This is the Cauchy-Reimann equation. Del u del x equals to del b del y, del u del y equal to minus del b del x. And our sufficient condition for fz to be analytic, here the complex function fz equals to u plus ib is analytic in a domain. There are two conditions. First one is the four partial derivatives. Similarly, that's why as it is del u del x, del u del y, del b del x and del b del y, it's denoted by ux, is denoted by uy and is denoted by v suffix x and v suffix y exist, and Cauchy-Reimann equation satisfied. This is the number one, and number two is the four partial derivatives here ux, uy, vx, vy all are continuous in that domain. Okay, these two are mainly necessary and sufficient condition for the fz function to be an analytic. Okay, so now we consider two problems. One for analytic function and other one is a Cauchy-Reimann equation. Number one, prove that the function fz equals to xy plus iy is not analytic function. So now solution fz equals to xy plus iy. Our fz means u plus ib form. All of you know u is the real part and v is the imaginary part. Now we are comparing these two forms. So our u equals to here xy and v equals to y. Now I have to find out del u del x, del u del y and del b del x, del b del y. So first del u del x. Del u del x means our function is u respect to x. So that's why other variable in that time our y, and y is a constant term. So del u del x equals to y. Del u del y equals to x. Del b del x, similarly v function with respect to y, this is 1, and v function with respect to x is y is constant, so 0. So our Cauchy-Reimann equation what? Del u del x, del b del y, del u del y equals to minus del b del x. These two equations if satisfy, then you call the Cauchy-Reimann equation as satisfy, and obviously function is called an analytic function. But here, well, if you see that del u del x not equals to del b del y, because our del u del x is y and del b del y is equals to 1. So that's why y is not equals to 1. So our contradiction arises. The Cauchy-Reimann equation here does not satisfy. So that means our function is not analytic. So therefore fz function is not analytic function. Since Cauchy-Reimann equation does not satisfy. Now next problem. Our next problem, for the function defined by fz equals to root over of mod xy, prove that the function fz is not differentiable at origin, but Cauchy-Reimann equation satisfying at origin. So there are two problems. First one is the differentiable does not exist at origin, and Cauchy-Reimann equation satisfy at origin. So first part, number 1, differentiable does not exist. So our formula is f dash z naught equals to limit z tends to z naught fz minus f of z naught divided by z minus z naught. This is the formula, differentiable at origin. So our z naught equals to 0, limit z tends to 0, fz minus f of 0 by z minus 0. So this is limit z tends to 0, fz is given, this is mod of xy, minus f of 0 is obviously 0 at origin, and z equals to x plus iy. Now let us choose a path y equals to mx along xy tends to 0, 0. This is the equation of the straight line passes through origin, and our m is the slope here. Therefore, limit xy tends to 0, 0 root over mod xy by x plus iy equals to limit our y equals to mx, so limit x tends to 0, x into mx by x plus I mx equals to limit x tends to 0, is x square, so only mod m root over mod m by 1 plus I m. This is our limit value. So total limit form is depends on m. So that's why our differentiable obviously does not exist. Why? Because this value is finite obviously, but this is not a unique. So that's why our differentiable does not exist, which is different for different values of m, different values of m. So limit does not exist. Limit exists means our unique value and always exist and also unique value, finite value. So limit does not exist, therefore differentiable f dash 0 does not exist at origin, does not exist. So first part complete. Our second part is Cauchy-Reimann equation satisfy at origin. Now start the second part, part 2. So our formula is, first you have to find out, obviously that's why Cauchy-Reimann means del u del x, del u del y, del v del x and del v del y. 4 partial derivative. Find out the 4 partial derivatives value. So first we have to find out del u del x. Del u del x formula is limit x tends to 0, f of u plus, this is the function of u. So u of x plus h y minus u of x y by h, because this is there are two variables. U is a function of here two variable. Why? Because our fz equals to root over of mod xy. Now to compare to u plus I before, now equals to here mod of xy, and v equals to, obviously there are no imaginary part, so v equals to 0. If v equals to 0, then obviously del v del x 0 and del v del y also 0. Del v del x 0 and del v del y also 0 because our function is 0. So now I have to find out del u del x. Del u del x at which point? At origin 0 0. So now limit x tends to 0, y tends to 0. This is limit h tends to 0, u h comma 0 minus u 0 comma 0 by h. Now limit h tends to 0, u of h 0, our u equals to mod of root over of mod of xy. So x is h and y is 0, so this is 0. 0 minus 0 by h, this is obviously 0. This is the del u del x, and del u del y equals to limit k tends to 0, u of x y plus k minus u of xy by k. This is our first principal form. Now find out at origin del u del y. So limit k tends to 0, u of 0, 0 plus k, this is k, u of 0 comma 0 by k. Now limit k tends to 0. This is obviously 0 because 0 into k is 0 and this is k. So obviously this value is again 0. So that's why our del u del x 0 and del u del y is also 0, del v del x 0 and del v del y 0. So our conclusion here is here del u del x equals to del v del y because all are 0 and del u del y equals to minus del v del x. It's a minus of 0 or plus 0, whatever. So that's why Cauchy-Reimann equation CRE, its short form, satisfied at origin. So done. Okay, students, I hope all of you understand this. So you remember our task is for today. First, number 1, prove that fz equals to, prove that the function fz equals to x plus I y square is not analytic. Number 2, for the function defined by fz equals to mod z square by z, z is not equals to 0 and 0, z equals to 0. Prove that the function fz is not differentiable at origin, but CR equation satisfied at origin. And last one, number 3, examine the function fz equals to z bar, number 1, and number 2, fz equals to z rez. Rez means our real part of z and z bar means our conjugate of z. To examine the function this differentiable or not at origin. Okay, student, this is your task. Okay, I hope all of you understand this. So today after this, thank you. Okay, bye students, have a good day.